For extra excitement, a new roller coaster ride is designed to launch the riders over an alligator-infested lagoon. The frictionless coaster starts at point A. The coaster lands on a ramp on the other side of the lagoon. Is the maximum height of the coaster after launch greater than A, or the same as A, or less than A? That is, does it do this? Does it do this? Or does it do that? Well, maybe that gets back on the track, but... So take a second, think about that, and then we'll talk. The actual path that it takes is going to be something like this, and it will go less than its greatest height, than its initial height. Why does it go less? Because at this moment, it had better still be moving this way with some velocity. So there is some kinetic energy associated with that point. But the total energy would be that kinetic energy plus whatever gravitational energy there was. From that height. So we can see that if I have this thing is this plus something else, this GPE must be less than that. But they're both proportional to height, so the height must be less as well. Change of tack. The energy stored in the deformation of a spring is an example of elastic potential energy. We'll talk about spring beginning with the magnitude of the force that a spring exerts. The spring resists deformation of size x with a force which is F sub s equals k times x, where k is something called a spring constant, because it's the constant that tells about the spring, and is measured in terms of newtons per meter. This is what's called a Hooke's law spring, or sometimes just simply ideal spring. Other kinds of springs might have different force laws, but generally if we don't say anything, we mean that the force is proportional to the displacement. As a quick example, we might say an archer pulls back on the string on a bow to a distance of 70 centimeters from the equilibrium position. To hold the spring at this position takes a force of 140 newtons. What is the spring constant in newtons per meter of the bow? We could do a really quick free body diagram. The person, if we imagine that the arrow has been done like this, the person is pulling back 140, and the spring is trying to get, the spring of the bow is trying to get it back to being unstretched. So they must be equal, which means that the spring force is 140 newtons. Therefore, K, which is the spring force over the displacement, is 140 newtons over 70 centimeters, which is 0.7 meters. And all of that comes out to be 200 newtons per meter. Now, in pulling on a spring, you exert a force, which means you do work, so energy gets stored in the spring. The energy stored in the spring object system, when the spring has been deformed by a distance x, is given by u sub s x equals a half kx squared. And you'll get used to this a lot too. We'll use this a lot. The energy in a spring is a half kx squared. Sometimes we abbreviate this as EPE instead for elastic potential energy. You'll notice it has a square in it, just like kinetic energy. That has some deep impact in thermo and statistical physics that we won't get a lot into, but is there. And anyway, it's otherwise pretty easy to use. We use it a lot like the way we've been using MGH, but of course it's a different formula. So, same archer pulling back the same string, so we know we have figured out that K is 200 newtons per meter, and we can use that. And we ask, what is the energy stored in the bow? But that's pretty straightforward. The energy stored in the bow, 1/2 times the 200 newtons per meter times the 0.7 meters quantity squared, which turns out to be 49 joules. A reasonable amount of energy, but not particularly huge. All right, in each case below, a block has been pushed against a spring on a frictionless horizontal surface, compressing the spring. The blocks were then released from rest, and at the instant shown, they are just about to lose contact with the end of the spring that had been compressed. The mass of the blocks and the force constant of the springs and the amount of these springs that were initially compressed are given for each system. Draw a blue circle around cases where the greatest kinetic energy at the start, at the instant shown, and draw a red circle around the cases with the least. We're going to use the idea that all of the initial potential energy becomes kinetic energy. So really, even though they're asking us about the KE, they're really asking us about the potential energy. And we know that the potential energy is 1/2 k x squared. So really, we just throw that into each of these. Like we say here, it's 1/2 times 5 newtons per meter times 0.4 meters quantity squared. And we do that for all of them. Doing that, we get 0.4 joules and 0.1 joule and 0.08 joule, 0.125 joules, 0.5 joules, and 0.125 joules. It's sort of important or interesting to look at that for D and F, they have the same spring constant and the same stretch. Therefore, they'll have the same energy, and it doesn't matter that the mass is different because the mass doesn't tell you how much energy is stored in the spring. Anyway, we can see pretty easily then that the 0.5 wins and the 0.08 is least. So E is more than A. It's more than D is F, which for some reason right here is bigger than B. All right, a circus performer on a skateboard is launched by a spring initially compressed at distance delta x as shown to the right. His speed on the horizontal portion of the ramp is v, and he rises to height h after he leaves the ramp. Draw a qualitative energy bar chart for the Earth skateboarder spring system as the skateboarder goes from the compressed spring position at rest to where he moves free of the spring on the horizontal surface. Put the 0 point at the height of the skateboarder before launching. So, with these things, the most important thing, or at least the best first step, is put down anything that you know is 0. So, for instance, he's launched from rest. Is launched from rest, so there's no kinetic energy at the start. And they tell us the potential energy is 0 there. And then after being launched, well, he has 0 gravitational energy because he's still at that same height. And the spring has entirely unwound, so that's gone to 0 as well. A last 0 that's less obvious is the work done. The only thing that acts on the skater in fact, that acts in the system at all, is the spring. The spring acts on the skater acts back on the spring, but those are internal to the system. There's nothing outside the system which is doing any work at this point, and so we can also say there's 0 external work. But that makes this almost trivial. Oops, sorry, misdirected something. Put the 0 in the wrong place. There's 0 gravitational energy. There is certainly some spring energy because the spring has started off compressed. So we should definitely have something in that box. And then after all is said and done, the thing's moving, but we know that this plus this has to equal this. So summing up all 4 of these columns, I have to get the same as if I sum up all 3 of these columns. So all of the energy that was spring energy has now become kinetic energy. All right, same problem, but now we're going to be asked to do it when the skater has actually gotten to his greatest height, h. And again, I would recommend let's put down things that are 0 that we know. So for instance, starts from rest, starts with 0 gravitational energy, ends at rest, ends with nothing in the spring, and there's no external work done because the system they gave us is the skateboarder, oops, sorry, hit the wrong one, the Earth skateboarder spring system. And since the Earth is included, then gravity is within this system, so there's no external work. So then our initial spring energy, whatever it was, has to turn entirely into gravitational energy. And so we get something that looks like this. New problem. A 40 Newton box is initially at rest on a smooth and frictionless horizontal surface. An unstretched spring with spring constant 10 newtons per meter connects the box to the wall. a 60 Newton force is applied horizontally towards the right. Complete the energy bar chart for the spring block earth system as the block moves a distance of 2 meters. Label the column heights. Set the 0 point for the gravitational potential energy at the center of the block. So, do we know of anything that doesn't change? Well, we know that we started off with 0 gravitational because I said do that. And the height doesn't change, so we end with 0 gravitational. At the start, there's nothing stored in the spring. And at the start, it's at rest. That leads you to some interesting things. All right, so we know that we will end up storing, let's see. We know that at stretching it 2 meters, how much energy is stored in the spring? 1/2 times k times the stretch squared. So 1/2 times 10 newtons per meter times 2 meters quantity squared, which looks like it's 20 joules. And we also know that the work done by the external force, well, us pulling is external because our system is the spring block earth. So this, whoever's applying that 60 newtons is not in there. And it's constant, so we know that's FD. 60 newtons times 2 meters, which is 120 meters. 120 newton meters, 120 joules. All right, so if I take the spring, and let's say that one little loop here is 20, then the external force is going to do 6 of those. 2, 4, 6, because 120 is 6 times 20. And again, we want to say, wait a minute, or at least think about these 4 columns have to equal these 3 columns together. So if we sort of do some labels, we had 120 here, and we have 20 here. So there must be left over 100 here, which would be 5 of these. So our final thing looks something like that.